Hello everyone, this is Tara Humphrey, the Titus Communications Manager, and I'd like to welcome you to our engineering webinar. We will begin the webinar in about 5 minutes, but I wanted to take this time to make sure that everyone's sound is working properly and give you a chance to adjust any volume controls you may have. If you have any sound issues though, please go ahead and enter them into the chat box on the right-hand side of the screen. And additionally, if you have any questions during the presentation, we'll be answering those at the end of the webinar. But I do recommend going ahead and entering those into the chat box as they come to you so you don't forget about them as the presentation continues. Again, thank you for joining us, and we'll begin in about 5 minutes.
Hello and welcome to our webcast. Today's topic will be selecting air distribution devices. My name is Jim Oswegen, Chief Engineer for Titus, and I'll be presenting today's program. I'll be joined later by Randy Zimmerman, who is also a Chief Engineer, and Mark Costello, who is a Product Manager for Grilles, Registers, and Diffusers. As a panel, we will answer any questions you may have. Covered in this presentation will be the ASHRAE guidelines for comfort, the effects of air distribution patterns on selection. We will also cover the common selection methods such as mapping, air distribution performance index, and perimeter applications. Finally, we will cover selecting devices to meet specific noise requirements. First, the comfort guidelines per ASHRAE Standard 55. The number in parentheses identifies the paragraph in the standard. Occupant comfort depends on the space temperature as defined by ASHRAE as the operative temperature, sometimes known as the dry bulb temperature. At the ideal operative temperature, the occupant will not notice any heat loss or heat gain from the adjacent space. Radiant temperature is the effect of warm and cold surfaces near the occupant. Local air motion, typically less than 30 feet per minute during heating, and less than 50 feet per minute during cooling, but may be higher where space temperature is increased. And the relative humidity, where there's no lower defined limit, but the dew point temperature must be maintained below 62.2 degrees Fahrenheit. Other factors impacting occupant comfort are the occupant activity level, known as the MET rate. For most office applications is sedentary or slightly elevated with casual movement about the space, and the occupant clothing insulation level, which varies between business casual summer attire consisting of lightweight clothing to more formal business or winter attire, which may include a jacket or a sweater. The zone of interest or occupied zone is defined by ASHRAE 55 as from the floor level to 6 foot above the floor, and more than 1 foot from internal walls, and 3.3 feet, or 1 meter, from outside walls, windows, or fixed HVAC equipment. Conventional overhead systems provide comfort through room air mixing. For this reason, these systems are also known as fully mixed systems. In a typical cooling application, 55 degree Fahrenheit supply air is delivered from a ceiling diffuser or a high sidewall grill. The mixing created by the outlet discharge jet results in room air motion. This so-called secondary air motion is due to the entrainment of room air into the supply jet where mixing occurs. Ideally, an overhead system results in a fully mixed air throughout the space with minimal temperature stratification. With a fully mixed system, the first thing that the supply air does is pick up heat from the overhead lighting. This is one reason why we typically need a 20-degree differential temperature on our supply air. The air distribution pattern also impacts our selection. First, we will look at a radial or circular air pattern. This pattern exists when the outlet distributes air equally in all directions. The impact on performance is that more room air is induced into the airstream and produces a well-mixed jet as velocities are reduced. Since the airstream is so well mixed, the jet will not lose surface effect and create drafts in the occupied zone. This pattern is well suited for VAV cooling applications. This smoke video shows a radial air discharge pattern. Notice that the air fills in the corners for an even discharge in all directions. Other outlets produce a directional or cross-flow air pattern. The diagram shows a four-way pattern, but it would be the same for a three-way, two-way, or one-way air pattern. The distance that an air jet travels to a given terminal velocity, say 50 feet per minute, will be longer with a cross-flow pattern than with a circular pattern. Because there is less induction when the velocity of a directional jet is reduced to less than 75 feet per minute, buoyancy will detach the jet from the ceiling, causing increased drop and potential drafts in the occupied zone below. Now, with the directional air pattern, the air leaves the diffuser with four individual jets. Room air may be induced into the airstream between the jets, leaving the smudging on the ceiling at the corners of the diffuser. The most common discharge air pattern from a linear slot or plenum slot diffuser is the crossflow. However, it is possible to produce a radial flow pattern by equipping the plenum boot with an optional pattern spreader. Supply grilles are less common today, but are very versatile. When air is discharged straight out with the horizontal and vertical blades set for 0 degrees, the air pattern will be the same as a directional flow from a ceiling diffuser. If the grill is located within 12 inches of a ceiling surface, a negative pressure region will occur above the jet, drawing the air back to the surface. This is sometimes known as Coanda effect. The surface effect will create longer throw and less drop. When the outlet is located 2 to 4 feet below the ceiling, the surface effect can be obtained by using the horizontal blades to direct the air upward at a 20-degree discharge angle. When the ceiling is more than 4 feet above the grill, it may be advantageous to direct the air upward 20 degrees to minimize the drop at the far end of the pattern, but without ceiling effect. The goal is to make sure that the air jet is still above the occupied zone at a terminal velocity of 50 feet per minute. If you're willing to sacrifice pressure and sound, the vertical blades can be used to spread the air to a 45-degree discharge pattern. This will create a radial pattern which will result in shorter throw and less drop. This will increase pressure loss by 70% and increase the NC by 7. Diffusers that have a built-in negative pressure pocket are identified in the Titus catalog with the insignia shown here. This means that these selected outlets, when used in an open ceiling layout, will still discharge air in a horizontal air pattern. Without a ceiling, the jet will entrain air on both sides. Thus, the throw to 50 feet per minute will be shortened by 30% from the catalog values. When an outlet without an internal negative pressure pocket is mounted more than 12 inches below the ceiling, the air will discharge downward at an angle of approximately 30 degrees. This will not adversely affect the comfort in the occupied zone if the 50 foot per minute terminal velocity remains more than 6 feet above the floor. Many times grills are mounted directly onto a spiral duct. For these cases, the main supply duct should be sized so that the velocity is less than 1,000 feet per minute. Personally, I recommend less than 800 feet per minute. It is also important that the grill assembly pressure loss be more than 1.4 times the velocity pressure in the main supply duct. For example, if the supply duct velocity is 800 feet per minute, the velocity pressure will be 0.04 inches times 1.4 equals 0.056 inches. So, if the static pressure loss of the outlet assembly is less than 0.056 inches, the outlet will become an inlet, and room air will be induced into the duct instead of discharging conditioned air into the space. Return grills come in many configurations. To maximize performance, a grill with a 0-degree deflection would optimize the sound and pressure levels. If it is desired to block the view into the duct, and you are willing to sacrifice some performance, select a grill with a 30 to 45 degree deflection, and the blades will block the view. Many other models, such as perforated face, egg crate grills, are available to meet aesthetic requirements. Return grill location. The system will operate more efficiently when the return grill is located in the stratification zone, which is near the ceiling during cooling mode and near the floor during heating mode. Since it is not practical to have multiple locations for return grills, the designer should choose the location that best fits their climate zone requirements. For example, in a warm climate like Dallas, an upper location is better due to extended cooling requirements. But if the building is located in a colder climate like Minneapolis, a low-level location may better fit the extended heating requirements for that climate zone. To provide consistency, most catalog throw performance data is shown with isothermal air, no heating, no cooling. When mapping, to assist with knowing the throw and drop from a cooling jet, there are 6 charts on the website and in the catalog engineering section, similar to the one shown here, to estimate performance. The various charts represent the results of cross-flow jets with and without sealing effect, and radial jets with and without sealing effect. These charts are especially useful for determining the drop from a cooling jet to make sure that the end of the jet does not penetrate the occupied zone at the 6-foot level. For additional assistance with mapping, we look at 2 charts. The first one shown here illustrates the results of an isothermal air jet. The top envelope of air shows a jet with 150 CFM leaving the outlet at 500 feet per minute. Note that the isothermal air remains on the ceiling at all terminal velocities. Also note that the location of the 150 foot per minute terminal velocity is at a distance of 9 feet. The lower jet is 300 CFM from the same outlet and reaches the wall, or in this case it could represent the collision point of 2 colliding airstreams, then turns downward till it reaches 50 foot per minute near the floor level. Note the jet reaches the turning point at or before the T100 distance. Now let's take a look at the effects of a cooling jet on the same airflows. The 150 foot per minute location of the cooling jet is approximately the same 9-foot distance as the isothermal jet. This is because the air is temperature independent above 150 feet per minute velocity level. Next, notice that the 150 CFM jet, when the cool air reaches a velocity of about 75 feet per minute, the jet loses surface effect and starts to drop off the ceiling, leaving the potential for drafts in the occupied zone in that area. Finally, for the 150 CFM jet, we see that the 50 foot per minute cooling distance is approximately the same as the 100 feet per minute distance with isothermal air. For the 300 CFM jet, because the air reached the wall or collision point before reaching the T100 value, the cooling jet has the same throw to 50 feet per minute as the isothermal jet. What happens when an air jet contacts an obstruction such as a beam or change in ceiling level? If the angle of incidence from the air jet discharge location to the bottom of the obstruction is less than 15 degrees, the jet will overcome the obstacle and be reattached to the ceiling. If the angle is greater than 15 degrees, dumping will occur at that location and may cause drafts below the obstruction. Air Diffusion Performance Index, also known as ADPI, is a method of evaluating occupant comfort during cooling conditions based on temperature and velocity in the occupied zone. This method has been in the ASHRAE Handbook of Fundamentals since 1967. The goal is to achieve an ADPI of 80 or above based on the effective draft temperature of the occupied zone test points. Team software can be used to calculate ADPI electronically. To do a test, which is described in the appendix of ASHRAE Standard 113, prescribes taking comprehensive survey of locations in the occupied zone at 4 specific locations. 4 inches above the floor, or ankle level. 24 inches above the floor, or waist level for a seated occupant. 43 inches above the floor, or neck level of a seated occupant. This is also the control temperature level in the space. Finally, the 67-inch level, or the neck level of a standing occupant. These elevations correspond with the temperature heights described in section 7.2.2 of ASHRAE Standard 55. Calculating the effective draft temperature for each data point includes the test point temperature T sub x. T sub c is the control temperature at the 43-inch level in the middle of the space, and V sub x is the test point velocity. The resultant draft temperatures are plotted on this graph with the acceptable points falling in the shaded parallelogram area. The number of points inside the parallelogram divided by the number of total test points determines the ADPI. While the goal is 80% or more, there is no direct correlation to ADPI and the percent of satisfied occupants. The chart also illustrates that stuffiness that is felt where there is no room air motion can be solved by lowering the temperature. The line across the bottom of the chart shows satisfaction with no air motion when the temperature is at or below design control temperature. The dashed line through the center of the parallelogram also shows a relationship between temperature and velocity of 15 feet per minute per degree Fahrenheit. So for each 1 degree rise in ambient temperature can be offset by adding 15 feet per minute to the room air motion. While it is important to know the ADPI for large spaces, if the space is conditioned by equal spaces such as a 20 by 20 module served by one outlet, the ADPI value for that module can be extrapolated for the space. To establish the ADPI, we must know the characteristic length, or L, of the module served. The L is the distance from the center of the outlet to the shortest edge of the module served, or 1/2 of the distance between 2 outlets. L is based on a 9-foot ceiling height and can be adjusted for lower ceiling heights or higher ceiling heights up to 12 foot. For example, when the ceiling height is 10 foot, add 1 foot to L. For outlet selection, we need to know the range of T50 over L that will result in ADPI of 80 or more. This chart shows results for several types of outlets and room load factors. The T50 over L is the catalog isothermal throw to 50 feet per minute, divided by the module characteristic length. The T50 over L is the bridge that gets us from isothermal catalog performance data to cooling conditions. A load of 20 BTUs per square foot is equivalent to 1 CFM per square foot at 20 degrees differential temperature. When using ADPI for design, if the system is variable air volume, select the maximum CFM to be at the top side of the T50 over L limit and the minimum CFM at the lower end. If the system delivers a constant CFM to the space, selecting the T50 over L in the middle of the range at the top of the curve is better performance. The next 2 slides will show ADPI comparison of 2 different types of ceiling diffusers. When we use ADPI, we want to know the range of CFM that will result in an ADPI greater than 80. On the top line of the Teams printout, we see that the ADPI for each airflow rate. We can see that the plaque face diffuser shown here, selected, will provide an ADPI of up to 450 CFM. The left side of the chart shows that the downturn is less than 150 CFM. In fact, ADPI will remain 80 or above down to 100 CFM. Note that at 450 CFM, the NC is 21. For comparison, we will look at the printout for a cross-flow perforated diffuser. The data shows that at 400 CFM, the ADPI is still 90, meaning that the maximum CFM for ADPI greater than 80 would still be a higher CFM. Note, however, that at 450 CFM, the NC is 37. This means that where NC 35 is specified, the performance tops out at 425 CFM. On the lower end of the perforated, it will turn down to 160 CFM and still be ADPI 80 or above. This does not make the perforated selection unusable, but has a more limited range to meet both ADPI and NC35 than the plaque-based diffuser. Let's look at perimeter applications. ASHRAE Standard 62.1, Table 6-2, is an important reference tool when selecting outlets for use on perimeter spaces where heating and cooling is accomplished from one ceiling diffuser. For a fixed geometry outlet, the recommendation is to direct 50% of the air across the ceiling, 50% down the glass. Table 6-2 shows, for spaces with a ceiling return, to be able to use an EZ factor of 1.0, the throw to a terminal velocity of 150 feet per minute must reach the 4.5 foot above the floor level, and the maximum temperature difference of the supply to room air must be 15 degrees Fahrenheit or less. When one of these conditions is not met, such as differential temperature greater than 15 degrees, the EZ factor becomes 0.8, which means you must supply 25% more ventilation air during heating conditions. Where overhead heating is combined with a floor return, meaning the return is located below the breathing zone, either low sidewall or on the floor, the EZ will be 1.0. The T150 reaching the 4.5 foot level also helps to assure that ASHRAE Standard 55 requirements for a maximum temperature gradient from ankle level to neck level of 5.4 degrees Fahrenheit is met. While the 15-degree delta T sounds scary to some, remember that to increase air temperature means to reduce airflow. Reducing the airflow means shortening the throw. 300 BTUs per lineal foot of glass requires 20 CFM per foot at 15 degrees, so 200 CFM will cover 10 foot of glass. We can improve the comfort level in the space and reduce the energy costs by supplying all the warm air down the glass during heating and all the cool air across the ceiling for cooling. This does not change the requirement for T150 and 15-degree delta T required by ASHRAE Standard 62.1. This smoke video of the auto changeover diffuser demonstrates the quickness in changing from horizontal cooling discharge to a vertical heating discharge. For the vertical discharge, the heat deflects back to the glass at an angle of about 10 degrees, allowing the mounting of the unit to be in the ceiling from 18 to 24 inches from the glass. This chart shows the results of lab tests comparing a fixed geometry diffuser with a 50-50 airflow on the red curve to an auto changeover diffuser directing all the air down the glass shown with the blue curve. The chart illustrates a warmer temperature in the space when the heat is all delivered down the glass. Data also shows a substantial energy savings because the conditioned air is delivered to where it is required. Both the 2009 ASHRAE Fundamentals Handbook and the 2011 ASHRAE Applications Handbook have useful chapters on room air distribution. For this section, however, I want to point to Chapter 8 in Fundamentals and Chapter 47 in Applications as resources for sound selection. ASHRAE Standard 70 prescribes the method of test used by manufacturers for air inlets and air outlets. For sound testing, the standard requires a minimum of 3 diameter equivalents of straight duct with a flow straightener to ensure non-turbulent airstream fills the duct at the entrance to the test device. Since these ideal conditions vary from most field applications, we will look at the impact of common field installations on the room NC. When does sound become noise? The answer is when it reaches a higher level than specified. When multiple sound sources, such as more than one diffuser, are located near the occupant, there's also an additive effect. Dampers located at or near the neck of the outlet will add to the sound level of that outlet. Less than ideal inlet conditions will increase the sound level of an outlet. This diagram shows two diameters of duct at the inlet of the diffuser. But since the flex duct is kinked, the airflow into the diffuser can become turbulent, increasing the sound level into the room. This hard 90-degree turn into the neck of the diffuser will mean higher discharge velocities in the direction away from the inlet, increasing the resultant sound level. This inlet condition will also modify the distribution of airflow from the outlet, with more air and longer throw in the direction away from the inlet, and less air and shorter throw back in the direction of the inlet. This chart shows a broad summary of research project RP1335 from the University of Nevada, Las Vegas. The transaction was presented to ASHRAE at the Chicago meeting. Multiple types of outlets from 3 manufacturers were tested per ASHRAE Standard 70, plus with a hard duct and flex duct at 3 diameter equivalents, 1.5 diameter equivalent, and 0 diameter equivalents, and fed with a 90-degree elbow at that height. All combinations were tested with and without opposed blade damper at the inlet to the diffuser. Under laboratory conditions, adding a damper added up to 5 NC. With 3 diameters of straight duct, the sound was just slightly higher than laboratory conditions. At 1.5 diameters, the sound increased by 2 to 4 NC, plus another 5 when the damper was installed in the inlet. With a hard 90-degree elbow on the diffuser inlet, the NC increased over the catalog was 5 to 10, but the damper did not create additional noise. An open damper increases noise levels up to 5 dB. Closing the damper increases the pressure ratio and increases the noise level even more. Some recommendations to minimize noise. Locate balancing damper as far from the diffuser inlet as possible. Provide as much straight duct, emphasize straight, into the diffuser inlet as the space will allow. Acoustic flex at the inlet will help attenuate unwanted airborne noise. Some concluding rules of thumb. When using a diffuser for exposed application, reduce the throw by 30%. For grills mounted on a spiral duct, maximum main air duct velocity 1,000 feet per minute and 800 feet per minute is better. Pressure loss across the outlet must be equal to the main duct velocity pressure times 1.4. Throw to 50 feet per minute with cooling is approximately the same as 100 foot per minute isothermal, except where the air jet reaches the wall at T100 or before, the T50 cooling will be the same as T50 isothermal. When the angle of incidence of an obstruction is greater than 15 degrees, the air jet will deflect away from the ceiling. There's a wide variety of products to choose from to match the user requirements. While architects desire pleasing aesthetics, engineers demand performance, and contractors are concerned with cost. The products shown here are popular because they are superior at providing the solution for multiple users. The panel will now answer your questions.